will be again an important result for us. This is feasible because first you will find this one and then differentiate. So just look on the second half. X1, X2, X3. This is X transpose and A is now if I multiply, I will get 1 by 3 matrix. I am writing here. This, and this. I think everybody knows the matrix calculation. One, two, three. The next step will be goes here. X1, A1, 2.
Plus? No plus. Oh, the next.
X1, A1, 2. And third step will be X3, A1, 3. X1, A1, 3. And now we have to differentiate it respect to look. Now we have to differentiate respect to X transpose. Because this is a row matrix and we have to take X in this direction now. So it goes like respect to this element respect to X1, then X2, then X3. This will go with respect to X1, respect to X2, respect to X3. This will also go with respect to X1, X2. If we check, this will give me A11. Here, respect to X2, what I will get? A21. Then A31. From there you can check respect to X1, I will get A12, then A22, A3. And if I do X31, I will get A31. I will get paid back. I will get paid back. That's a little bit confusing, because I was doing it in this direction.
Yeah.
So, but I put answer in this direction. Ultimately, let me write down the result. The important result is the derivative of X transpose A respect to X transpose, we get this. Right. one is A transpose X.
I think you don't need that. You can just go.
Okay.
Yes.
Actually, I was thinking to give the exercise just to prove this one. If you want, we can just try.
No, I mean, you know A is, you just substitute A as A transpose. That's it.
Yeah. But the thing is, the dimension should be matching. If A is 3 by 3 and this is 3 by 1, then it will work. And if the dimensions are not matching, you can't go ahead. So all the I have put all the results. What I have proved. If you want, I can go for this proof. But it's the same thing.
Yeah, it's just
Let us go with product rule, where I was stuck last time. We have to find out the derivative of, say, fx and gx. Normally what we do for the product rules, we differentiate both the things one by one. Means one time we have to find out the derivative of g and one time we have to find out the derivative of x. But what to do with the rest of the part? For that thing, there are two methods. I will explain one by one. In first case of this one, he has taken both f and g as n into m matrix. Sorry, m into n matrix. F of x and g. Because both of same size, so this will not work. So he has started with this one. The book has given the rule using transpose of f and g because both are vectors. Suppose f1 goes like f1, f2, f3 up to f1, and g1 goes like g1, g2, g3 up to g. And the x is having the dimension xn. And xn is a vector of from x1 to xn. Now, according to this rule, if we have to find out the derivative, this derivative will be equals to we will take the transpose of this one and we will differentiate the first one plus then we will take the transpose of first one. I didn't find this proof anywhere, but we know by normal calculus that whenever we have to find out the product rule, we have to differentiate two things. What we do, we just we do the differentiation one by one. So here it's done. Function this derivative of f and derivative of g, and rest of the things they put in such a manner so that it is comfortable with the another one. It can be multiplied.
You can show that also, right? Last time you almost saw it already. I mean, it's not hard at all. But it doesn't matter, we don't have time.
Okay. On this basis, if we have to solve the derivative of actually ax, suppose we have to find out the derivative of this one. Now, this is a quadratic kind of term. Normally, ax square is not, you won't find ax square in matrices because if x is a matrix, x into x is not possible unless, until and unless x is square matrix, because its f is say 3 by 2. So you can't multiply a 3 by 2 with a 3 by 2. So that's why ax square is not possible. So they kept it in this manner. Okay.